So now let us discuss resistivity. So resistivity, it's the basic property of the material, and resistivity is a measure of the resistance of a given size of a specific material to electrical conduction. So based on this resistivity, you can categorize materials into three parts, and that is, first part is for first category is you can say it's a conductor, and second one is semiconductor, and third one is insulator. So now I'm writing resistivity of different materials at 0 degree at 0 degree centigrade. So let us take a conductor. Copper is an example for conductor. So resistivity of copper at 0 degree centigrade is 1.7 into 10 to the power minus 8 ohm meter. This is the resistivity of copper. So similarly, if I write resistivity of one semiconductor, let's say silicon, that is 2.3 into 10 power 2 ohm meter. And if you take one more material from insulator, fused quartz is an example for insulator, and for that resistivity is order of 10 power 16 ohm meter. So based on this resistivity, you can categorize materials. So if resistivity is very low, you will say that materials are called conductors. If resistivity is very high, then we say the materials are called insulators. If resistivity is in between conductors and insulators, we call them as semiconductors. So all these resistivities I wrote at 0 degree centigrade. At 0 degree centigrade. So this is for copper, this is for silicon, this is for fused quartz. This is for fused quartz. So this is the resistivity, and these are the resistivities of different substances, different elements, different materials at 0 degree centigrade. But this resistivity is not constant parameter. As the temperature changes, resistivity also changes. So let us look at how resistivity of copper changes with temperature. If you look at resistivity of copper with the temperature, and now I am drawing the graph for that. So here I am taking temperature, and here I am taking resistivity, and this is a conductor, so resistivity will be very high, and the order will be 10 power minus 8, and the unit for that will be ohm meter. So now here 0.2, and there it is 0.4. So here 50, 100, 150, and I am taking temperature scale in temperature Kelvin scale. So as we increase temperature, then resistivity goes like this. It goes like that. So this is the resistivity is not constant, and it is changing as temperature is increasing. There is change in resistivity, and that's not a constant. And this is for copper. If you take one more element called nichrome, this is for copper. For example, if you take the same thing, temperature versus resistivity for nichrome, and nichrome is an alloy. Nichrome is an alloy. Is made of nickel, iron, and chromium. So, and the resistivity is order of 10 power minus 6 ohm meter. And now here I am taking 1, and that's 1.1, and that's 1.2, and temperature scale is 200, 400, 600, 800, and so on. So as you increase temperature, again resistivity increases, but it goes from here to somewhere like this. See, look at this, the difference between these two graphs. and there is no linearity here because specific resistance or resistivity is not changing linearly with temperature, and here the specific resistance is changing linearly with the temperature, and also the variation is very less for high range. For example, if temperature is going here from 0 to 800 degrees centigrade, 800 Kelvin, the change in resistivity is very less. But here, when it goes from 0 to 150, there is a huge variation in the resistivity. And resistivity of nichrome is not highly sensitive to the temperature, but resistivity of copper is highly sensitive to the temperature, and the resistivity of nichrome is not highly sensitive to the temperature because of this reason, and this nichrome is used to prepare or to manufacture resistors. And let us take one more thing, that is resistivity of a semiconductor. If you take a resistivity of semiconductor maybe for silicon, then resistivity of semiconductor decreases as temperature increases. And I'm not writing any scale here, this is simply a qualitative graph just to say that as you increase temperature, resistivity is coming down. It means conductivity is increasing, and here resistivity is increasing with temperature, conductivity comes down with temperature. Conductivity reduces with temperature, conductivity comes down, conductivity decreases with temperature. So now we can explain all these by the equation, that is, say we know the resistivity is reciprocal of conductivity, and we know conductivity as a n e square t by m. So then the reciprocal of that will be m by n e square t, and here m is mass of the charge, and e is a charge of an electron, and t is relaxation time, and n is number of charged particles per unit volume. So as you increase, let us explain why conductivity or why resistivity is increasing with temperature in case of conductor. So let us see that. So here resistivity is increasing with temperature. See, as you increase temperature of the system, as you increase temperature of the conductor, there will be no appreciable change in n. Number of charged particles per unit volume remains same with temperature. But relaxation time comes down because as temperature of the system increases, then lattice vibrations increases. As temperature of the system increases, then lattice points vibrates more rigorously in the system. When lattice points vibrates more rigorously in the system, then electrons, the collision probability of an electron with lattice point increases. When collision probability of an electron with lattice point increases, relaxation time comes down. When relaxation time comes down automatically, because everything is constant except this T, and T is with temperature, T is coming down. When T is coming down, then rho increases. So that is the reason. And here also the same thing. And here, in case of semiconductor, as you increase temperature, resistivity is coming down. So in this case, initially there are no free electrons. As you increase temperature, and some electrons will be free, or maybe some electrons may go from valence to conduction band, and so in that case then n increases. When n increases and rho decreases, that's all. When n increases and rho decreases, and the effect of T will be very less when compared to n, because initially there are no free electrons. As you increase temperature, number of free electrons increases. When number of free electrons increases, if effect of T is very small when compared to that, then rho decreases. That is the reason. When rho decreases, conductivity increases, right? So in case of metals, in case of conductors, as you increase temperature, resistivity increases, conductivity decreases. In case of in case of semiconductor, as you increase temperature, resistivity comes down, but conductivity goes up. So this is and one more, let us look at one more material, that is, for example, let us take a mercury. In case of mercury, now this is temperature and this is resistivity. As you increase temperature, we know that resistivity increases. From here, let us start from the room temperature, and it goes like this. So when you decrease the temperature, then resistivity also comes down. But when temperature comes to 4.2 Kelvin, suddenly the resistivity comes to 0. So resistivity of mercury is 0 at 4.2 Kelvin, right? So now when you increase temperature above the 4.2, and you will have non-zero resistivity, and when the temperature at which the resistivity goes to 0 is called critical temperature. The temperature at which resistivity goes to 0 is called critical temperature, and critical temperature for mercury is 4.2. So here, when it comes here, resistivity is 0. When resistivity is 0, then conductivity must be infinity. So it means if you take any, so these materials are called superconductors. Superconductors. So in case of superconductors, resistivity will be 0, but conductivity will be infinity. So it means, for example, if you take a superconducting loop like this, once you establish current in this direction in that way, then even you look at the same system, after long time, the same current will be going through that. So current persists in the system for long time. So this is the superconductor, and mercury behaves like a superconductor once temperature is below 4.2 Kelvin, and 4.2 Kelvin is the critical temperature for mercury. So now let us write down resistivity of any material at particular temperature. So let us use, see, we know from here resistivity is continuously changing, and even it is not, it's continuously changing, and even it is not linear to the to this linear in this graph, right? So it means if I draw a graph between resistivity and temperature, and that is, if I draw a graph, the graph is not a linear. The graph is not, it means that the variation of resistivity is not equal for all interval of temperatures. That's the meaning. So now if I take a small interval, for example, if I take a small interval in this graph, for example in this interval, so the temperature variation may be this part, and see in this small temperature variation you can take it as a roughly a straight line, roughly linear, roughly linear. And so whenever your temperature range is very small, you can write down temperature, you can write down resistivity at particular temperature, let's say T equals to resistivity at reference temperature T0, or maybe you can write like this. So, or let us write clearly, so rho T equals to rho T0 into 1 plus alpha T minus T0. So if temperature range is very small, you can use this equation. You can use this equation, and here T0 is reference temperature and T is temperature at any temperature, and alpha is here temperature coefficient of resistivity. This is called temperature coefficient of resistivity. Temperature coefficient of resistivity, and rho T0 is resistivity of the material at reference temperature, and rho T is resistivity of the material at temperature T. And we know that the resistance of the material is equals to rho L by A. So here resistance, R is resistance of the material, and rho is resistivity, and L is length of the material or length of the wire, and A is area of the wire. So as you increase temperature, then resistivity changes. When resistivity changes, R must also change. Let us neglect the effect of length and area. For example, as you increase temperature, if you find there is no appreciable change in L and A of the material, if you find no appreciable change in length and area of the wire, then you can write down, from this equation you can write down R is proportional to rho. From here you can write down that R is proportional to rho. When you write R is proportional to rho, then you can also write that R of t equals to RT0 into 1 plus alpha t minus T0. So this equation is for temperature variation. So as you increase temperature, resistance of the material also increases, and here the resistance of the material increases with temperature linearly. This graph shows that. This graph also shows the linear, because you are taking a small portion. If you take a big portion, this equation cannot be true. If you take a small portion, this can be true. And now if I fix, let us take my range is a 0, and now I'm taking my range as a 0 and 100 degrees centigrade. If I take my range as a 0 and 100 degrees centigrade, so I'm taking my temperature range is 0 and 100 degrees centigrade. So already I got equation, that is R of t equals to R T0 into 1 plus alpha t minus T0. This is equation what I got. So I'm fixing my reference, I'm taking my range from 0 to 100 degrees centigrade. So when you take reference temperature is 0 degrees centigrade, then resistance of the wire, for example, if resistance of the wire at 0 degrees centigrade is, let's say, R0, and resistance of the wire at 100 degrees centigrade is, so resistance of the wire at 100 degrees centigrade is, let us say, R100, and at temperature T, resistance of the wire is, let us say, RT. So let us try to get one link here. So let us use first this one. Resistance of the wire at temperature T is RT. Let us write that, RT. That equals to resistance of the wire at 0 degree centigrade is R0 into 1 plus alpha, then T minus T0. T0 is 0 and T is T. So you get this. And next one, you take resistance of the wire at 100 degree centigrade. Resistance of the wire at 100 degree centigrade is R100. That equals to resistance of the wire at 0 degree centigrade is R0 and 1 plus alpha, and T is 100 and T0 is 0, then you get here 100. So this implies RT by R0 minus 1 equals to alpha T, R100 by R0 equals to 1 plus, minus 1 equals to alpha 100. So this implies RT minus R0 by R0 equals to alpha T, and here R100 minus R0 by R0 equals to 100 alpha. So when you divide these two, if you take this by that, that gives RT minus R0 by R100 minus R0, that equals to T by 100. So that implies T equals to RT minus R0 by R100 minus R0 into 100. So this is one equation. So for example, if I know resistance of the wire at 0 degree centigrade, if I know resistance of the wire at 100 degree centigrade, if I measure the resistance of the wire in a lab, maybe temperature of the lab is T, then I can able to measure the temperature inside this lab. I know resistance of the wire at 0 degree centigrade, I know resistance of the wire at 100 degree centigrade, and I also know resistance of the wire in the room at room temperature. Then from that data I can able to find out what is the room temperature. So this is about your resistivity and resistance. Now we know resistivity, and we know the resistivity is a measure of the resistance of a given size of the specific material to electrical conductor. So you can choose different materials for manufacturing resistors. So resistors of different values are commercially available for domestic and laboratory purpose. And these resistors are of two types. And the first resistor, now here, and these resistors are of two types. So first type is wire wound resistor, and in this wire wound resistors are prepared by winding nichrome or manganese wire. Why I am choosing nichrome and manganese wire? So nichrome and manganese, these are two materials whose resistivity is uh, almost the same, or you can say the resistivity is highly insensitive to the temperature. If the resistivity is highly insensitive, then resistance of that material will not be altered when there is change in temperature, when there is a fluctuation in temperature. And by using this, you can prepare resistors of few ohms to and a few hundreds of ohms, few hundreds of ohms. And if you want to get high range resistance, if you want to get high range resistance, then we will go for carbon resistors. So in this, a carbon with a suitable binding agent is molded into a cylinder, and wire leads are attached to the cylinder, and the entire thing is kept in a plastic jacket. And this is a compact and very cheap. Because of this reason, these resistors are widely used in electronic circuits. And you can also find out resistance of these resistors by using color code. For example, if I have a carbon resistor in this way, let us say this is the resistor, and there will be color coding on this resistor. So 1, 2, 3, 4 colors. So assume that first color is red, and second color is also let us say red, and third color is also red. Let us say final color is silver. Then how to find out resistance of this resistor? So to find resistance of this resistor, and this is the code to identify that. Let us look at a table to identify the resistance of these. Let us look at the table here. So let us look at the table here. So the table I am drawing here. So the colors I am writing first. The colors are, first color is black, and the second color is brown, third color is red, and fourth color is orange, fifth color is yellow, next is green, next is blue, next one is violet, next one is gray, next one is white, next one is gold, and next one is silver. So this is the color, and now let us write digit here, digit, and next one is multiplier, next one is tolerance. So digits are, for black color it is 0, for brown color 1, 2, 3, 4, 5, 6, 7, 8. For white it is 9. So multiplier also 10 power 0, 10 power 1, 10 power 2, for this color 10 power 3, for that color 10 power 4, for this color 10 power 5, for blue color it is 10 power 6, next 10 power 7, 10 power 8, and for white color it is 10 power 9, and for gold color it's 10 power minus 1, for silver color it's 10 power minus 2. Tolerance is not given for all colors, and tolerance is only for gold and silver. For gold, tolerance is 5% and silver 10% tolerance. So now let us try to find out resistance of this resistor. So here there are four colors. So in four colors, the first two colors gives the significant number of the resistor. So resistance, significant number. So first color is red. Now let us look at first. These are two digits. You can say these are two digits. Next one is multiplier, decimal multiplication. This one is multiplier, and final one is tolerance. And so first one is red color. Then what is number for red? Red number is 2. Then 2. And next is also a digit. So that is also a red color. Then you can hide once again 2. And third one is red once again. That is multiplication. No, that is multiplier. That's 10 power 2. So into 10 power 2. And final color is silver. For silver tolerance is 10%. See here. It's 10%. So it means plus minus 10% ohm. So you can write down this as 2200 plus minus 10% means in this 10% is 220 ohm. So it means that the resistance of this resistor can be 2200 plus minus 2220 ohm. 10% is the 10% can be a maximum variation in this resistance. So that's called tolerance. So this is what resistance of this resistor. So now let us take one more. Let us take one more resistor. Let us identify what is the resistance of this one. So this is the resistor. Now first color is, let us say, yellow. Next color is, let us say, green. Next color is, let us say, blue. And let us say final color is, let us say, gold. Then what is the resistance of this resistor? So then first two gives the significant figures. So first color is yellow. Look at yellow number. It is 4. Next color is green. That is 5. Next is multiplication. That's blue. That is 10 power 6. Then final color is gold. That is the tolerance. Plus minus 10%. And sorry, for gold it is 5%, not 10%. It's 5%. 5% is the tolerance. So 5% ohm. Now next time I will give the resistance of the resistor. Then we need to estimate, we need to guess what are the colors. So I have a resistor here. There are 4 colors, 1, 2, 3, 4. I don't know what colors are there, but I'm giving resistance of this resistor. From that we should able to estimate, we should able to guess what are the colors. So now let us say 3, 6 into 10 power 2 plus minus let us say 360 ohm. So from here, so let us write down this part. So 3 means, first these are the two significant figures, then 3 means then color must be orange, 6 means color must be blue, then multiplier is 10 power 2, it means that's red color, and then look at the error, tolerance is exactly 10% because this value is 3600 plus minus 360 ohm. This is exactly 10% of this. 10% means it must be a silver color. Sometimes the fourth color may be missing. Sometimes fourth color may be missing. For example, look at this diagram. Red, yellow and let us say blue. There is no fourth color. For this case, whenever fourth color is missing, you have to take tolerance as 20%. If there is no color, you have to take it as 20%. So in this case, red color, first a significant figure 2, and next one is yellow. For yellow it is 4, and multiplier is blue, that is 10 power 6. Then there is no color next color, so it means plus minus 20% ohm. 20% ohm. So this is how we can find out resistance of different wires. Now let us discuss a few problems on this. The first problem is calculate the drift speed of an electron when 1 ampere of current exists in a copper wire of cross section 2 mm square. So consider, first problem is, consider a copper wire. This is the copper wire and it's carrying current I equals to 1 ampere, and area of the wire is 2 mm square, and number density or number of free charged particles, number of electrons per unit volume is also given, that is 8.5 into 10 power 22. If this is the case, then what is the drift velocity or what is the drift speed of an electron? So now we know that I equals to NE AVD. This is the general equation. From here you can write drift velocity equals to I by NEA. So we know what is I and we know what is N, we know what is E, we know what is A. From all these values you can able to guess what is VD. So I value is 1 ampere by N value is 8.5 into 10 power 22. Charge of an electron is 1.6 into 10 power minus 19. Then area is given as 2 mm square. So it means 2 into 10 power minus 6 meter square. So that equals to roughly 3.6 into 10 power minus 5 meter per second. So this is the question. So now let us take one more problem. The problem here is an electron moves in a circle of radius 10 centimeter with a constant speed of 4 into 10 power 6 meter per second. Find electric current at a point on the circle. So this is the problem now. An electron is moving in a circular path in this way. Then radius of the circular path is given as 10 centimeter and it's moving with a constant velocity, that is 4 into 10 power 6 meter per second. Then we need to find current at any point, maybe at this point. So electron is going in this way. Then we know when electrons are moving in particular direction, the same effect you will see when positive charges are going in opposite direction. So then we know the flow of positive charge is called, or rate of flow of positive charge is called current. So current will be moving in this direction. If charge is moving in that way, current will be in this direction. So that current will be here equals to Q by T, and T is time period of the revolution, and Q is charge of an electron, so that is E is only crossing this area. So T is 2 pi R by T, so that 2 pi R by V, that V you can write here. So I know what is charge of an electron, we know what is velocity, and we know R also. So once you substitute all the values, I equals to 1.6 into 10 power minus 19, and that V is 4 into 10 power 6 by 2 into 3.14 into, then R is 10 centimeter, it means 10 power minus 1 meter. So once you calculate that, your answer will be roughly 10 power minus 12 ampere. So that is the current. So now next question. The question is, a wire of length 1 meter and radius 0.1 mm square has resistance of 100 ohm. What is its specific resistance? So the question is, there is a wire of length 1 meter and radius 0.1 mm, and resistance of the wire is also given as 100 ohm. then we need to find what is resistivity. So we know equation, that is R equals to rho into L by A. From here you can write rho equals to RA by L. So R we know, R is 100, and A we know, because R we know, from R we can find out A, that's pi R square, then R is 0.1 mm. It means 10 power minus 4 meter. So when you take square, then it will be 10 power minus 8 by, that is 1. So once you compute this, your answer will be 3.14 into 10 power minus 6 ohm meter, because this is 10 square, that is 10 power minus 8. So when you cancel, you get 10 power minus 6. So this is answer. So the next question is, the current through a wire is given by I equals to I0 plus alpha t, where I0 is 10 ampere and alpha is 4 ampere per second. Find the charge crossed through a section of wire in 10 seconds. So now this is the wire, and current going through this wire is given by this equation, I0 plus alpha t, and I0 value is given and alpha value is also given. I0 value is given as 10 ampere and that is 4. This is 10 ampere and that is 4. Then your I becomes 10 plus 40. This is what your current is, the current going through this wire. So now we want to find what is the charge that is crossing through a section of wire in this wire, let us say. So in 10 seconds. So now you can write down I as dq dt, then dq dt, then dq dt equals to 10 plus 40, then dq equals to 10 dt plus 4t dt. That implies, to get total charge that is crossing this area in 10 seconds, you have to integrate this function. So 10 dt from 0 to 10 seconds plus 4 t dt from 0 to 10 seconds. So this is 10 into t. When you apply boundary conditions, you get 10 into 10, 100 plus 4, that is t square by 2 we get, t square by 2. Then t square means when you apply boundary conditions, it's 100 by 2. So then answer will be, because here 100 and there it is 200, then total answer will be 300 coulombs. So 300 coulombs is answered. So the next question is, a current of 1 ampere exists in a copper wire of cross section 1 mm square. Assuming each copper atom provides 1 electron to the system, and calculate drift speed of an electron, and density of copper is given as 9,000 kilogram per meter cube. This is the copper wire. This is the next question. This is the copper wire and it's carrying current 1 ampere. Copper wire is carrying current 1 ampere and area of cross section, area of the wire is 1 mm square. So this is copper wire, and density of the copper, mass density is 9,000 kilogram per meter cube. So now we want to find out what is drift speed. So we know equation for drift speed is, we know that current equals to NEAVD, that implies drift speed equals to I by NEA. So in this, I is given, that is 1 ampere, and area is also given, and the charge of an electron we know, then we need to guess what is N. And from this data you can able to guess that. So we know the atomic mass unit is 63.5 for copper. So it means if you take 63.5 gram of copper element, there will be Avogadro number of atoms. So that is 6 point something, say 03 or whatever, into 10 power 23 number of atoms will be there. So when you take 9,000 kilogram, then how many atoms will be there? In 9,000 kilogram, then how many elements will be there? So once you find n here, because our condition says that each atom is providing one electron. So if you are able to guess number of atoms in this mass, then the same number of electrons will be there. So whatever you get n, the same thing will be number of free electrons. So that once you calculate these, you can cross multiply and you can calculate that, then the number of entities will be roughly 8.4 into 10 power 28. So once you get that, you can substitute all the values here. So now your Vd equals to I is given as 1 and n value is 8.4 into 10 to the 28 into E is 1.6 into 10 power minus 19, and area is given as 1 mm square. It means 10 power minus 6 meter square. So that implies the final answer roughly will be equals to 7.4 into 10 power minus 5 meter per second. So this is the answer. Now look at the next problem. Find the resistance of hollow cylindrical conductor of length 1 meter. The inner and outer radius of cylinder is 1 mm and 2 mm respectively. And the resistivity of the system is given as 2 into 10 power minus 8 ohm meter. So now the problem is, this is a hollow cylinder and inner radius is given as 1 mm and outer radius is given as 2 mm, and length of the cylinder is given as 1 meter and resistivity is given as 2 into 10 power minus 8 ohm meter. So you need to guess what is the resistance. So we know by this equation that R equals to rho into L by A. So rho we know, L we know, then area you have to find out here effective area because it's a hollow cylinder, so there is nothing inside, so only this is your area. So the effective area will be equals to here pi R2 square minus R1 square, because this is your R2, this is your R1. So when you take R2 square minus R1 square, so because R2 we know and R1 we know, then area becomes pi times, then R2 square is 2 square and R1 square is 1 square, that is 3. You get pi 3 mm square. That will be your area. So now resistance is rho is 2 into 10 power 8 into L is 1 by area is 3 pi into 10 power minus 6, because it is given in terms of mm square. So when you take in meter square, you get this answer. So now that will be equals to roughly 2.1 into 10 power minus 3 ohm. This is answer. So now look at next question. The next question is, resistivity of platinum wire at ice point is 5 ohm and at steam point is 5.39 ohm. When the resistance of the same wire is measured in the laboratory and it is giving as 5.12 ohm, find out temperature of the lab, temperature inside the lab. So now when you take platinum wire and resistance at 0 degree centigrade is R0, that is 5 ohm, and resistance at steam point, that's at 100 degree centigrade, is R100 equals to 5.39. Now the resistance of the same wire is measured in the lab also, and say temperature of the lab is T, and that is RT, the resistance is RT, that is 5.12. Then you have to find what is the room temperature. So now you know equation, that is RT equals to R100 minus RT minus R0 by R100 minus R0 into 100. So RT minus R0, RT is this and R0 is this, so it is 0.12 by R100 minus R0 is 0.39 into 100, so that equals to 31 degrees centigrade. This is answer for this. So let us look at the last question, that is resistance of an iron wire and copper wire at 20 degrees centigrade are 3.9 ohm and 4.1 ohm respectively. At what temperature will the resistance be equal? Alpha for iron and alpha for copper is given. So now, resistance of, let us take first one is iron, second one is copper. So it means R1 means it's iron, R2 means it is copper. Then let us say R, you can write down R1 at temperature T equals to R1 at a reference temperature 20 into 1 plus alpha 1 into T minus 20. This is the equation. Similarly, for second wire, R2 at temperature T equals to R2 at 20 degrees centigrade, that is a reference temperature, 1 plus alpha 2 into T minus 20. See, in this case, as you increase temperature and this increases and that also increases. So at some point, the increment may not be same, but at some point this value may be equals to that value for particular value of temperature. That temperature we need to guess. So for that, if you equate these two, then I get R1 20 into 1 plus alpha 1 T minus 20 equals to R2 20 into 1 plus alpha 2 into T minus 20. So R1, this we know. This one is, this value is, 1 means iron. So let us write data here. I'm writing data here. Then resistance at resistance of first wire at 20 degrees centigrade, reference temperature is 3.9 ohm. R2 at 20 is 4.1 ohm. Then similarly, alpha 1 is, alpha 1 is iron, so alpha 1 is 5 into 10 power minus 3 Kelvin inverse. Similarly, alpha 2 equals to 4 into 10 power minus 3 Kelvin inverse. Here alpha 2 means copper. So in these two equations, we know what is R1 and what is R2, and we know what is alpha 1 and what is alpha 2. Once you substitute all the values, let us substitute 3.9 into 1 plus alpha 1 value is 5 into 10 power minus 3 T minus 20 equals to R2 value is 4.1 into 1 plus alpha is 4 into 10 power minus 3 into T minus 20. So everything we know. Once you simplify this equation, then you will get, or let us simplify this. You can write 3.9 plus 3.9 into 5 into 10 power minus 3 T minus 20 equals to 4.1 plus 4.1 into 4 into 10 power minus 3 into T minus 20. So once you forward this 3.9 here and that one here, then you will get, now I'm forwarding this here, so you get 0.2, and now I'm forwarding this part here. So here T minus 20 is common, and even 10 power minus 3 is also common. Then this value is 19.5, and that value is 16.4 into 10 power minus 3 is common, T minus 20 is also common. So that implies this value is 3.1 into T minus 20, that equals to, so once you send this one here, it will be 200. That implies T minus 20 equals to 64.5. Then T equals to 84.5 degrees centigrade. So this is the answer. So that's all. For next time we will discuss batteries, internal resistance of battery, and what is EMF of battery, etc. Those things. So thank you.